So this course is being offered on NPTEL by the course instructor Professor Digvijoy from IISc Bangalore, from the Science Department of IISc Bangalore. And this is the schematic of the this is the outline showing what we have covered till now. And if you can see that these first four sections have been covered till date. These four, and we have covered introductory, the RF devices, heterojunction physics, which this particular section covered some of the things which will be covered in today's lecture, just like if you talk about the HEMTs, the gallium nitride, algan HEMTs, and some of the basics about 2D electron gas. But we will go into the deeper physics of what these things are in these particular devices. And we talked about some of the high frequency, high power devices, which are some are junction based, some are junctionless devices that work on certain exotic effects like quantum tunneling and gun effect, basically in order to give the negative resistance. So negative resistance we studied about in order to amplify the signal. So these are used as microwave amplifiers. Okay, now we are going into, and in the last section we talked about some 3-5 FETs, particularly something called as MESFETs, which is gas based MESFET, which looks something like this. You have a n-doped gallium arsenide, let's say, and you have a gate, you have a source, you have a drain, and then you have modulation of the channel. The channel is already present, and you apply the negative voltage in order to repel those electrons and in order to deplete it for the conduction to stop. Okay, so that's why the threshold voltage is negative in these cases. Okay, because you need to turn off the channel. Okay, so that means these are depletion mode transistors. Depletion mode FETs. I should call FETs, field effect transistors. Okay, now what else are we going to talk about in today's lecture? So today's lecture will be about 3-5 high electromobility transistors. We will study about modulation doping. The modulation doping, we will study about 2D electron gas, a very interesting effect in these high electromobility transistors, and we will study briefly about its breakdown, about the gain, and maybe somewhat about small signal model of these microwave high electromobility transistors, and that is what we will be trying to cover in this particular session. So I can see nobody has joined till now, but pretty much this lecture will be available online, so you don't need to worry, you can anytime watch it. Okay, so I believe my internet is a bit slow today, so I'm going to turn off my camera for a brief moment, maybe, so that I can see whether there is any improvement in the internet, because I can see that there is a lag in the voice, and as well as whatever I'm writing. Okay, so I'm briefly turning off my camera. Okay, so let's talk about what we are going to cover in this session, and particularly in this session, I will be having questions in between it. So outline of this session. So what is the outline of this session? The outline is what are we going to cover today in today's session. First of all, we will cover what is something called as modulation, doping, and we will cover about HEMTs, which are 3-5 based high electron mobility transistors, but this will be particularly gallium arsenide, aluminum gallium arsenide based HEMTs. GaN, algan based HEMTs will be talked in the next lecture. Particularly, we will talk about scatterings. We'll talk about scattering. We'll talk about how it affects the mobility. We will talk about, let's say, resistances that is related to the scattering events, resistances, and we will talk about a little bit of band diagrams, and I believe, is my internet working? Yeah. Okay. So we'll talk about about band diagrams. Then we will talk about, let me check, this goes and we will talk about some design parameters while designing the microwave based circuit of these particular devices. We will talk briefly about noise, maybe some figure of merits like noise figure and noise factor, as well as noise figure, which are the logarithmic of one another. And we will talk about here we will talk about these heterostructures. Okay, so now what are we going to cover? Now, how are we going to cover it? Now, let's first of all talk about. Let me just add a few more pages here. Add a page. Add a page. All right. I guess there is some issue because my internet is lagging. I don't know why. Let me just uh, close certain things. Why is this lagging so much today? Okay, I guess I need to. Okay. So there was some issue with it, but I'm going to re-log in. Okay, so there was some issue with it, but I have re-logged into this thing. So let me start again, and then we will basically move forward. Okay. Okay, let's talk about first about high electron mobility transistors. Basically 3,5, but gallium arsenide, aluminum gallium arsenide based 3,5 devices. Then we will jump into what is the modulation doping in these particular devices. So you know that if you have a aluminum gallium arsenide, if you have a gallium arsenide, because they are two different materials with two different band gaps. Let's say this is Eg1, this is Eg2. So Eg2 is greater than Eg1. Then you know that when you join these two materials, when you deposit them one over the other, the band diagram is going to look something like this. So there will be a bend at this particular position. This will remain same, Eg1, Eg2 will remain same because it's a material property, it's not going to change. And in here, because this particular gallium arsenide is unintentionally, unintentionally, it is slightly n-doped. Okay, so the Fermi level is going to be closer towards the conduction band, and when you draw the Fermi level in this system, it will look something like this. So you can see that at this particular position, the Fermi level has crossed the conduction band of gallium arsenide, and this is aluminum gallium arsenide. This is gallium arsenide. Okay, now what is going to happen? Now there are certain phenomena that happen at this particular edge, where you can see the conduction band of the gallium arsenide has gone below the Fermi level. And you know that whenever a conduction band of, let's say, that whenever the conduction band goes below the Fermi level, that indicates this particular region has very high density of electrons. High density of electrons. That is from your basic device physics course. The high density of electrons. And that is the same case here, except that not only is the conduction band going below the Fermi level, there is a huge barrier on the other side. This particular barrier on the other side of the conduction band, and this is basically a potential barrier. Okay, so this is a potential barrier, and it is now a similar problem like that of a quantum well, except that this quantum well, if you zoom this region here, it looks something like this. So this is almost like a triangular quantum well, where if you talk about this is the Fermi level, then if you solve the Schrodinger equation for it, you solve the Schrodinger equation for it by considering the potential term in the Schrodinger equation as, like, let's say some a into x, where a is some constant and x is a linear function of x. X is a linear function of x is vx equals to x is just a linear function of x. Okay, because you know that this potential profile, this particular potential can be approximated as a straight line. Okay, so you can write it as some ax term. Now you need to put this potential term back into the Schrodinger equation in order to solve it, and you get a wave function solution, which is something called as Airy wave function solution. Airy wave function solution. So you can solve it. It's just a differential equation you need to solve. You can solve it either numerically. You can solve it either numerically, or you can solve it, maybe there are certain analytical approximations of it. Okay, now, what are those AD solutions? AD solutions look something like this. If you have, let's say, this as first, now you know because there is a quantum well, so it will have a well-defined energy state, discretized energy state, just like in a potential well, in a square potential well or a rectangular potential well, you might have taught about in fundamental courses. If the potential outside is infinite, if this is zero, you have the discretized energy levels. This is E0, this is E1, E2, so on and so forth. So similarly here you have E0, then you have, let's say, E1, then you have E2, then you have E3, and when you as you go higher and higher, these the spacing between the energy levels become closer and they become a continuous energy states as you go higher in the energy states. Okay, so that is the property of this particular triangular potential well. Okay, that comes up because of the solution of the Schrodinger equation. Now you see that here, if you have this as the Fermi level, now you see the ground state. This is the ground state is below the Fermi, is below the EF. By how much amount? Let's say this is some. Let's say this is some. Let's call it VDI. Let's call it some VDI, where this is maybe how how deep is E0 from the Fermi level. Okay, now this VDI is very important parameter. We will look up it in upcoming slides why this VDI is important, but it basically gives you the information about the overall parameters which we need to extract from the band diagram. Okay, that's what we are going to look in the upcoming slides. So now what is going to happen? What will happen is that if you talk about this particular structure, let's say you have a triangular well and you have the Fermi level here. Let me not draw this. You have the Fermi level and you have the first eigenstate, first energy state below the Fermi level, and you call this particular difference as VDI. Let's say let's call it some VDI, which represents how how deep is the E0 from EF. Okay, so we're talking about triangular well here, just what we have studied from the previous basics. Now we are going to evaluate it, but before that evaluation, we talked about this particular structure where we have gas and L gas. We joined them and we got this particular band diagram, and we zoomed it into the triangular potential region where we have something like discretized energy states, and this is how the zoomed in triangular potential barrier looks like in a GAN L-GAN structure. Now what we have now, the first of all, when you have, let's say, you have a L gas, you have gas. Now, if you, let's say, dope it with certain material, something called as modulation doping. What is modulation doping and why it is necessary? Modulation doping. What you do is that you dope this particular section and you leave this particular section without any doping. So you dope it with, let's say, Nd, whatever is the N plus doping for aluminum gallium arsenide. You dope this section and you leave this particular section as without doping. So now when the channel forms, so when you combine both of them, you get a band diagram something like this. Okay, where this is the EG of gallium arsenide, and you see that these particular when you dope this particular region, you have ionized impurities and you have electrons. Those electrons will go now down the hill and they will come down here, and because you have a confinement here, you have the first energy value, you have the electron density which looks something like this. So now let's zoom into this particular region, because now the pink electron has come from the impurities of the aluminum gallium arsenide. It is different than what happens in GaN algan based structures. In the GaN algan, if you remember, if you have an aluminum gallium nitride and if you have a gallium nitride, and if you combine them, their electrons basically come from the surface states of the GaN. Surface states of GaN. How they come up? Because L-GaN and GaN are highly polar materials. They are polar materials. And there exists two type of polarization. One is spontaneous polarization, another is piezo polarization. Okay, so they bring up electrons from the surface states of the GaN, which are present here. They are donor type surface states. Okay, donor type surface states. Those donor type surface states donate the electron. They settle up between the GaN-L-GaN interface and result in the form of two-dimensional electron gas here. Here it's opposite. Here you have doped the L gas region. Those doping have released those electrons. They are donating the electrons, and those electrons are settling in the two-dimensional electron gas at this particular region, which is this accumulation, basically accumulation of electrons, accumulation of sheet of electrons. So that's why the if you write the charge density, you write it as per centimeter square here, not as per centimeter cube, because it's a two-dimensional sheet charge, two-dimensional electron gas. I've talked about this, why it's called as two-dimensional electron gas. Two-dimensional is because the carrier is confined in one direction. Carrier is confined in z direction. What does z direction mean? If this is the z direction, this is the growth direction, then the carrier cannot move in this direction. It can move in x, it can move in y. And how does that look like? Let's say you have a wafer. That is how gallium arsenide or any other gallium nitride looks like. It comes as a wafer, a circular wafer, disc-like shape. And this wafer has certain thickness, you know it. This thickness is very small because this is the growth direction. You grow it from top to bottom. Okay, you grow it from bottom to top. You start growing certain layers. First you have one layer, then you have another layer, then you have another layer. So that's how you grow the heterostructure. So now if you let's say if you cross section it, if you cut it here and see what is basically inside, you have now this cross section looks something like this. You have this layer, you have L gas layer, and then you have gas layer. So I've drawn it thick intentionally so that you can understand. So this is now L gas layer and this is gas layer. Okay, so we have cut that wafer, and this is the top view I'm showing. Obviously, in the top view, the thickness won't be visible. I have shown the thickness in order to make you understand. This will be the front view of the wafer. Most of the people are confused about how the electron gases look like, or where is the electron gas and how the material behaves. So this is the thickness of the wafer, which is basically the thickness of gallium arsenide plus the aluminum gallium arsenide and other layers, if there are any buffer layers or any other layers, so you see that two-dimensional electron gas will be present exactly here in the front view. And in the top view, the two-dimensional electron gas is present throughout. Okay, so you need to understand that fact. Because in the front view, you are seeing only it as a layer, as a line. But on the top view, when you see it on the top, it is present throughout below the aluminum gallium arsenide layer. So it's present throughout. Okay, so now what happens is that the electrons, because of the 2D nature, because of the carrier confinement in the z direction. So now what is the z direction? This particular direction is the z direction because it's the growth direction. Growth direction. Can you please turn off your mic?
this is the growth direction which I'm talking about. So it has its own coordinates. It can be 0, 0, 0, 1, which are the Miller indices, how you have grown the particular crystal. Okay, or it can be any other crystal coordinates. So now a carrier cannot move in the z direction because of the 2D confinement. Okay, so electron is not able to move in this direction. So this direction is not I should say a movable or allowed direction for the electron to move because of the confinement. But electron can move in this direction, or electron can move in this direction. Okay, particularly that means in here, if we show it on the wafer, electron can move in this direction, electron can move in this direction, but it cannot go in and out of the wafer, okay, in the growth direction because of the carrier confinement. So that is what the direction means, and that is what basically it this particular wafer shows how the electrons are moving. So that's why, if you, let's say, because this is the front view, of the gallium arsenide, or these HEMTs, high electron mobility transistors. So that means if you connect a, let's say, if you connect a contact here, a metallic contact, and if you connect a contact on the bottom, and if you, let's say, give any voltage supply here, you won't have any current flow, because the electrons cannot flow throughout, because the electron cannot flow in the z direction. Okay, electrons cannot flow in this z direction. Okay, on the other hand, if you take this particular wafer, if you duplicate it, if you take this wafer and you make a contact here, which is, let's say, the source, you make a contact here, which is the drain, let's call it source drain, you connect some maybe potential, you will see there will be a current flow because the electrons are now going to flow. Okay, so now that is the basic fundamental of how these devices work. So these carriers are confined in the z direction, and they are able to move in x and y direction. And electron gas, electron is, it's a particle. And now, what is gas? Gas is just like a degenerate gas. It is a term used for whenever there's a huge density of electrons near the Fermi level, something called as Fermi sea. It's just like a sea of electrons. Okay, so there is a huge density of electrons, and it's almost as if it's almost like a metal. So in a metal, you don't draw a conduction band, you show the Fermi level only, because most of the electrons are populated near this region. Okay, so whenever you gives any kind of excitation to a metal, those electrons go in the higher energy regions, basically little bit above the KT, a little bit above the Fermi level. Okay, the similar reasoning applies here. You have the confinement, you have the triangular potential well, you have the Fermi level, you have the first energy state, eigenenergy, you have the second eigenenergy state. As you go on, you have the third, and it becomes continuous as you go on up above the conduction band of this, as you go in higher and higher energy states. And then you can have its the solution basically of the Schrodinger equation, which is the psi as a function of x, looks something like this. This is something called as 80 wave function solution. So this is the wave function, how it looks like. It's almost like a Gaussian, but not purely Gaussian. It peaks around the center here, center of this well, which is something called as centroid. And you can basically find how much is the distance of the centroid. And mostly in the literature, you call this distance as delta d, which is the distance of the centroid of the charge at which it peaks from the surface, from this particular surface. Okay, from the interface of aluminum gallium arsenide. Okay, so now this is for E0. Now, as you go higher and higher in energy, the solution, the wave function solution looks something like this. If you go for the higher energy, the wave function solution looks like this now. Okay, now you have two centroids, and as you go higher, you have three centroids, so on and so forth. This is just like a solution of a Schrodinger equation in the potential well. Okay, just like you have a rectangular potential well, you have energy levels, and you let's say this is a finite potential well. This is a finite potential well. This is, well, I should say, an undergraduate problem in physics. So you solve the Schrodinger equation for it. You get the solution in n equals to 1, n equals to 2, n equals to 3, something like this, which is shown in this particular picture. So these are the solutions. These are basically the wave functions, psi of x. And you can square this particular wave function in order to find the probability of electrons in these wells. And if you know these psi mod square, you can approximately compute the electron density, which is directly proportional to mod psi square. Okay, this is directly from the quantum mechanical aspects. Okay, so this can, even if you know the mod psi square, you can compute the sheet charge density. Okay, but there is another way to compute the sheet charge density, which is basically electrostatic, considering the electrostatics of these devices. By considering the fields, by considering the potentials, the charge density, you can compute this particular ns, which is the charge density. Okay, and here it also follows the same logic. You have this particular part, you have this particular part, which is the evanescent decaying part. Evanescent decay means this is moving, tunneling out of this barrier. So this is called as evanescent decay. So this is the solution. This comes from the solution of the Schrodinger equation. Okay, so this is an exponentially decaying part, and this is basically the tunneling part. Tunneling part, and similar happens here. If you see this particular section, let me draw it like this. This particular section is basically evanescent decay. It is decaying out of this particular region, out of this confined triangular potential well. And sometimes it creates a problem. Sometimes when you do experiments, it can. This is basically leaking part. The wave function of the electron is leaking into the band gap, and you might have certain then there is a probability of finding the electron in the band gap there. Okay, because you see that if you have the band diagram which looks something like this, then if this is the first energy level, you have the electrons, and that means this particular there is a probability of finding the electron near in the band gap region. So this is sometimes problematic, but let's not talk about this here. Okay, so let me okay. So this is about how the two-dimensional electron gas looks like, and this was about if you dope it using this something called as modulation doping. Modulation doping. Now, what does it do? Why is it important? Why doping is important? That was the main question which we posed initially. Why do we dope it in a modulation fashion? Now, you see that whenever you dope it in a modulation fashion, you dope it slightly away from the interface. Okay, the interface forms here, so it's away from the interface. Now, what happens because of it? Because of it, you see, when you have doped this particular region, you have doped this particular region. That means you have the positive ions, which are Nd plus ions. They have donated the electrons now, and those electrons have settled in this particular confinement region. Okay. Now what? Now what happens is that it actually it becomes or I should say it uh, reduces the interaction of these positive ions with the electrons. Okay, so the concept looks something like this. If you have a normal semiconductor or any semiconductor, if you dope it uniformly with n-type dopants. Okay, let's say this is any semiconductor. So if you dope it uniformly, that means you doped it uniformly with the n-type dopants. So you'll be having positive ions, background ions, and you will be having electrons. Okay, because you have doped it n-type. Had it been doped with p-type, you would be having negative ions and holes. Okay, so now what happens when the electron moves in this particular crystal? There will be there will be scattering because of these positive ions. You see now, because there's a this is a negative charge, then this is a positive charge, so there is a coulombic attraction forces, coulomb forces coming into picture. Okay, so from the basic Coulomb's law, F equals to minus k q1 q2 over r square. So the Coulombic forces come into picture. And now you want the electron to move straight in a straight line, just like normal balls. You don't want them to scatter here and there. Now, what happens, because these dopants, these positive ions, they are randomly arranged in a crystal, and even if there is certain periodicity, then what is going to happen is that if this is a positive ion, this is a positive ion, the electron wants to move, there will be scattering. There will be basically these Coulombic forces come into picture. There will be attraction of these positive electrons with the positive ions. So it may go here, then it may go here, then it will go on the in the other direction. So that is how electron tries to move. So this is something called as scattering. Okay, scattering. And particularly this has been given as a name as impurity scattering. Impurity scattering, because you see that these dopants, these are basically impurities, impurity atoms. So that's why it's called as doping, because they make the original sample impure. They make the pure sample as impure by introducing these scatterers, by introducing these doping agents. Okay. So now what does it do? You see that whenever this scattering event happens, it randomizes the momentum. It causes something called as momentum randomization. Randomizes the momentum of electrons. So let's say the electron was going in this direction with some momentum k1, it changed its momentum, now it's going in this direction, then in this direction with momentum k3. So it totally randomizes the momentum, which is basically the product of mass into velocity. But for the electron moving in the crystal, it's the product of h bar times k, where k is the wave vector if you consider it to be moving in a crystal. Okay, so this is something called as crystal momentum of the electron moving in a crystal. Okay, so let's not talk about that momentum. What is the difference between the crystal momentum and the actual momentum? But it totally randomizes the momentum of the crystal, of the electrons. Now, what does it mean? What is going to happen? Now, because of it, initially you thought of electron to be moving like this. Now it's moving in a randomized fashion throughout the crystal, and that is basically what happens is that it impedes the motion of the electrons. Okay, so this is basically this, it impedes the motion of the electrons, impedes the motion of the electrons. And you know that the mobility basically is related to the electronic charge, the something called as momentum relaxation time divided by the effective mass. This is the relation of the mobility. Okay, under certain approximation, obviously. So that means if you have if your momentum relaxation time is affected, your mobility is going to get affected. Similarly, if your, let's not talk about effective mass, if your effective mass increases, the mobility will reduce. That sounds logical. But what is this momentum relaxation time? This is something called as momentum relaxation time. So whenever the electron undergoes any scattering, let's say this is positive ion, again positive ion, electron comes here, goes here, it's again scattered, goes here. So that, let's say this is the distance between the two scattering events. Let's call it L. Okay. So that this particular, there will be some time spent between these two scattering events, between the momentum randomizing events. Let's say electron is moving with velocity v electron, then v electron will be L over, let's call it tau. Then this tau will be given by L over v electron velocity. So this is something called as momentum relaxation time, tau. So it's the time with which the, basically between the two successive collision events. Okay. So whenever the electron tries to move from this place to this place, then it moves to the other place. So this particular length and the time spent between these two events is basically something called as momentum relaxation time. And this denotes the mobility. Okay. Now you want this particular time to be more so that your mobility will be more. Okay. What does that mean? That means you want this length to be as more as possible, as long as possible. You don't want the, in other words, you don't want any momentum relaxation events in the, for the electrons. Okay, so if you can just maybe, if you can stop the electron or gather the electron at this particular position in your, at the drain end, then there is only one scattering event present and it has gone into the drain. Let's say what I'm telling is, if you have a source, you have a drain, and if the electron is moving in the channel like this, let's say this is a gate, and what is going to happen if, let's say, there is a one positive ion here, one positive ion here, another positive ion here. If the electron is moving like this in this fashion, so it has undergone a scattering event. Now let's say you have made it in such a way that if you have a source, you have a drain, and you have only, let's say, one positive ion here, what is going to happen? Electron will come, undergo a single scattering event, and then directly go into the drain instead of multiple scattering events. So what is going to happen? The mobility in this case will be greater and the mobility in this case will be lower, because here the scattering is low as compared to that of this particular thing. Okay, so that is one concept, and that is necessary because it's going to affect the mobility. And why is this particularly important here now? So this particular thing is important here had because we have moderately doped this particular region away from the interface, this particular region away from the interface. Now, if you bring this particular region, or let's consider the scenario that this overall thing was doped uniformly instead of modulation doping. Let's If this was uniformly doped, what was going to happen is that you would have same positive charge, positive charge, positive charge, which come from the donor, and electrons here. And because there is a channel present here of the electron sheet, which is the sheet charge, whenever the electron was going to move, it would face these scattering events. Okay, so the electron is going to move either in and out of the screen. Okay, it's not going to move in the right and left direction because there is confinement there. So in the device level, what is going to happen if this is L gas and this is gas and this is two-dimensional electron gas, which is this region. So electron can move in this direction, it can move in this direction. Let's consider electron moving towards the right direction. So what is going to happen if you don't have modulation doping? You have positive charges then here, positive charges, then electron will encounter these scatterers and it will again randomize its momentum, and more the momentum randomizing events, less will be the mobility. So more momentum, let's call p and as a vector is momentum randomizing events, more the momentum randomizing events, the mobility will reduce. That means the device is going to suffer. Why the device is going to suffer? Because the current is directly proportional to the mobility. So you want the electron to move faster through this channel. But if you have uniformly doped the entire aluminum gallium arsenide L gas layer, then this particular thing is going to drastically reduce the mobility. Now how does this particular scenario come to rescue is that if you dope it using modulation doping, you dope it away from the interface so that these particular impurity centers are away from the channel, so that there is some distance, let's call it d, between the doping region and as well as the channel, so that electrons can freely move in and out of the uh, I should say screen, or in other words, electron can move in these two particular directions freely without any scattering. And that is the concept of the modulation doping. And important thing here to note is that if you have, let's say, this structure again, where this is the conduction band of the gas, this is gas, this is L gas, and let's say this is the Fermi level. Oops, not here. It should be the N type in gas. Whenever you draw the Fermi level, you have to make sure you draw it correctly, because it should not mean the other thing. This is N-type because this is N-type gas unintentionally. So this is the Fermi level. It's slightly near to the conduction band compared to that of the valence band. Let's draw it clearly here. And when you compute using the Schrodinger equation, you compute the first eigen energy of this well, E0, let's call it E0. It looks like this. This is the charge density profile. And now what you have is that you have doped this region and you have impurities in this region, and this particular distance is d. Okay, and the distance from the centroid of the charge density toward the interface is delta d. Okay, and the difference in the energy between ef minus e naught, let's denote it as something like vdi. Okay, so now what happens? The another possible scenario is that there can be remote screening effects. What is meant by remote screening effects? Even if these scatterers are at certain distance of d away from the sheet charge, they can remotely affect it, because at the end of the day these are charges, and if you separate the charges, there will still be repulsions or attractions between the charges. Okay, you have certain charges and you separate it by certain distance, you know that there will be certain forces. Okay, between these two charges, coulombic forces. Okay, so that's why you have to be at appreciable distance away from these charges so that they don't affect each other, you by those coulombic forces. Okay, so that's why this particular d distance is important whenever you modulately dope it. And you know that f falls as 1 over r square, so you have to accordingly manage this particular d. How you are going to ensure that the channel electrons uh, do not get, I should say, do not get scattering events from these particular impurities. So that is the important thing in modulation doping. Modulation doping. Okay, now there is one more concept. There is one more concept called as delta, something called as delta doping. Delta doping. Delta is the delta charge. It's a Dirac delta function. So if you have a band diagram like this, like this, and you draw the let me draw the Fermi level. Not again. It should be like this, and then you have like this. Okay, so this is the Fermi level. Now, instead of doping it, instead of doping it like this, using something called as modulation doping, you can use another way of selectively dope it at a particular region with a very high concentration of doping. What I mean to say is that you can selectively dope this particular region with very high concentration of Nd positive ions, Nd, let's say Nd doping, and you call it something called as Nd plus, which means it's a very highly doped region, maybe of the order of 10 to the power 17 to 10 to the power 19 per centimeter cube of N-type acceptors, N-type donors in this particular aluminum gallium arsenide region. So what it does now, definitely there is a charge, then it's going to modify the band diagram. Okay, and and from your basic device physics course, let's say if you have a p-n junction, you have not, let me draw the p-n junction. You have a p-n junction, you have the p on this side, you have n on this side, you have positive ions, you have negative ions, and you have something called as depletion region. Whenever you draw the charge profile of this, let me call this as the center, which is the metallurgical junction. You have a positive charge here, you have a negative charge here. Okay, so this is the charge density, how the charge density, so this axis is rho as a function of x, this is x, so this direction is x. So this is how the charge density looks like. Okay, this is positive charge, so this is q nd plus, this is q nd minus, na minus, not plus. Okay, so then you using the Poisson equation, you have dou E over dou X is rho over epsilon. So you integrate this particular thing and you get a electric field profile, something like this. Now you do the similar scenario in case of something called as metal oxide semiconductor field effect transistor. If you have MOS structure, metal oxide, this is semiconductor, and you know that if you have this particular oxide layer here, you have a semiconductor, let's say this is n-type semiconductor, and you have a metal here with certain Fermi level, and when you join them, you get maybe a structure like this, where the Fermi level, not like this, where the Fermi level runs through the middle and it's flat at equilibrium. That means there is no net flow of the charges. Why am I drawing Fermi level like a crazy thing? Okay, let's knock it like this. Has to be close to conduction band because the bulk properties cannot change. Okay, this is EF, EV. So this is the Fermi level of metal, and this is what happens if you draw a band diagram of this particular structure, MOS capacitor in equilibrium, obviously. And now what is going to happen? Then here you might be knowing that if you consider, let's say, a trap charge inside the oxide, a positive trap charge or a negative trap charge, it modifies the band diagram by bringing this particular band down at this particular position and then bringing it up. So here is the positive charge, so the band bends down at this particular position. So what it means is that it lowers the electrostatic potential energy of the electrons, because consider an electron here now. So now positive charge is definitely going to attract the electrons. So electron would love to basically live at this particular place because it has a mutual force of attraction, attractive force towards the positive charge. So that's why the band bends down, and you have a little type of bend like this, so that electron can allowed to live at this particular place near the positive charges. Okay, so that's what happens here. Whenever you delta dope this particular region, whenever you delta dope this particular region, you have a bend in the band, and the bend looks something like this again. And then you have the other things going in a similar fashion. Okay, so this is gas, this is L gas, and you have this particular bend where you have delta dope. Okay, why the band is inverse and why not the band is like this is because these are positive ions. These are positive ions from n-type impurities. And then you have the other usual things, which is the let me join this thing. Let me have metal. This is the metal Fermi level. Okay, so now this is the scenario. Maybe I have not drawn this to the scale on this side. Okay, because this thing should be, let me draw it partially. Not this. This will be like this. This will be like this. And the Fermi level in equilibrium should be flat. You have to ensure it every time that in equilibrium this is flat without I should say violating uh, any of the principles, without violating that this particular material should behave as it is in the bulk. Okay, here the Fermi level is crossing the conduction band is crossing the Fermi level. The Fermi level is flat in the middle, and here this particular distance should be less because it's an n-type, not distance. The energy difference should be less. EC minus EF should be closer. Okay, EC should be closer to the EF because it's n-type on this side. So you have to ensure it every time while drawing the Fermi level. So this is the overall band diagram now. So it looks like there's a banding in the middle, and then there is a two-dimensional electron gas which is present at this particular position. So that is what we have talked about in the previous slides. Now what? Now what happens is that, let me add few more pages. Okay, yeah. So now what is going to happen? Now we have further bendings. We have bending first here. Let's call it this as V1. This is another bending. Let's call this as V2. And this is, I guess my screen stopped. What happened? Oops. Is there any problem with the internet? Is this thing misbehaving? Yeah, yeah, I just noticed it. I think at what point did you lose this track of the screen? Were you able to see this particular thing and whatever I said?
Yes, yes, right now it is visible.
Okay, sure. Thank you. So okay, I lost the screen and I'm going to continue from this point. And I don't know what happened. Okay, so I hope it's recording. Yeah. All right. All right. So what I was saying is that now you have uh, certain voltage, certain energy dips in the energy band diagram, which you need to compute. And why do you need to compute it? We will see in the upcoming slides why it's necessary to compute these particular things. But most of the things you might have covered from the previous lectures. This particular thing, let's call it, this is a Schottky barrier between a metal and a aluminum gallium arsenide layer. And another thing is here this particular barrier, which is delta EC, which is the offset energy conduction band offset between the L gas and the gas layer. Okay, now you need to compute it using the same principle which we basically talked about in the first lecture. So what was that principle? The principle was simple, that you need to start at from single Fermi level, and then you need to go above, and then you need to come back to that particular point in a loop fashion in order to compute whatever are the factors you want to compute. What I'm saying is that maybe it was a very long statement. So if you have a band like this, why am I messing with the Fermi level? It cannot be like this. Let me draw it to the scale. What? Let me draw it. No, the Fermi level. Let me draw it like this, and let me bring it here. Let me draw the Fermi level like this. Okay, now it looks fine. This is the Fermi level from on the metal side. Now you know the these particular bendings, the Schottky barrier, which is 5e, the V1, V2, the conduction band offset, and the and you also know this particular thing. Let's call this the difference between the Fermi level and the E0, which is the first eigenenergy of the two-dimensional electron gas. Let's call this difference as VDI, which is basically how much uh, deeper is the first eigenenergy from the Fermi level. Okay, so now you have all other things. You have the phi b, you have this as V1, this difference as V2, this as E, not this, this whole is basically EC. Okay, because this is the conduction band of the gallium arsenide and this is the conduction band of the aluminum gallium arsenide. So this difference is the conduction band offset. Okay, and this particular thing, let's call this as this particular thing is VDI, and this is the Fermi level as usual. Now, what you need to do in order to compute something called as sheet charge density as a function of gate voltage. Why this is necessary? Why do you need to compute the sheet charge density as a function of gate voltage? Because at the end of the day, you want to turn the field effect transistor on and off, and because these are depletion mode devices, that means you need to apply the gate voltage in order to repel these electron layers to turn it off, because electron layer is this is already present there. Whenever you don't have any voltage applied, this electron layer is already there. That means the device is, I should say, this channel is already existing there. Okay, now what you need to do, you need to apply something at this terminal in order to flatten this band, in order to repel these electrons or deplete these electrons, so that the channel will turn off, so that the device will turn off, and you will have the control of turning the channel or turning the device on and off. So that is why this is called as depletion mode transistor. In the normal MOSFET devices, which are mostly enhancement mode, you always you don't have the channel, you create it by using the gate. But here it's the opposite scenario. So that's why the threshold voltage is negative here. The threshold voltage is negative. You might have seen this in MESFETs also in the previous lectures in, I think, the week 3 or week 4. Okay, so that's why it's necessary for us to compute the what happens to the sheet charge as a function of gate voltage. So that's why what we are going to do is that we are going to compute it by computing the voltages, just like going through a loop, starting from the Fermi level, starting from this Fermi level, and going towards the going towards the higher end, going towards this V1, going towards the V2, then coming down, then coming back at this Fermi level, so that a loop can be finished. It's just like summing all the voltage and then equating them to zero, because this is all in equilibrium, remember. Okay, so there will be no net flow of the charge, there will be nothing. Okay, this is just in equilibrium. Okay, now what is going to happen? The thing will the what is going to happen is that if we let's say apply some gate voltage now at this particular point, because we have to find this as a function of gate voltage, so gate voltage has to come into picture, otherwise there'll be the ns will not be a function of gate voltage if you don't apply anything. Okay, so when you apply the gate voltage at this particular terminal, you apply the negative voltage here, you apply the positive voltage here. Whenever you apply the negative voltage, the electrostatic potential energy on this side rises, it increases. Okay, so what is going to happen is that, let me remove this, let me remove these things, let me draw it in blue. So this will go up like this will be like this will be moving higher, and this will be like this, so that you have a reduced this well at this particular region. So okay, so this is the behavior of the band diagram when you apply the negative voltage on this side, because negative is going to bring everything on the left hand side towards the higher electrostatic potential energy. Okay, so that's one thing, it's going to go higher. Now you do the same exercise, that is you loop over all of those things and come back to the Fermi level and sum all the voltage and equate them to zero. So what I mean to say is that if you let's make a convention, if you go above, if you go in the up direction, while you sum up the voltage, you choose not negative, you choose a positive sign, and if you come down you choose a negative sign. So that is the convention we are going to follow. You can just reverse it, just the convention, but you are going to arrive at the same solution. It doesn't matter. So that is what initially we have the gate voltage applied, which is negative. So let's write minus Vg, and then we have the Schottky barrier. The Schottky barrier, because we are going up, so we will write the Schottky barrier phi b, because its energy we will divide it to the charge to make everything in the potential terms. Okay, because energy is minus q times v. This is energy, this is potential. So you can write the potential as minus e times q. Okay, so this is for the electrons. And now you go down by v1. You came at this point, now you go down by v1. The down sign is negative, so you write minus v1. And then you go up again by v2. So v2 is positive because it's you are going up. And then you have the difference of the conduction band offsets, basically this particular delta ec and this particular delta ec. Because you are going down, now you have delta ec again divided by q, because it's you have to convert it into the voltage. And then you are going up again by how much amount, vdi, which is the difference between the Fermi level and the first energy level of the energy level inside the 2D electron gas. So all of this equate to zero. Okay, all of this summing all the voltage and equating them to zero. Now what are the things you get? Now you have to rearrange the things. You have to just do the rearrangement. And what are the things in this that we know? Basically we need to compute this vdi. We need to we know the Schottky barrier, which is basically has certain relation with the conduction band of the aluminum gallium arsenide. And this conduction band offset will remain there. And we need to basically find what is this particular vdi, which is the difference in the Fermi level of the gallium arsenide with respect to the first energy eigenstate. So how do you compute this particular thing? Okay, let's consider this triangular well again. Let's consider this triangular well again. And this is the Fermi level. I'm drawing only this part. This is the first energy eigenstate. First energy eigenstate. This is the 2D electron gas, E0. This is EF minus E0, which is Q times VDI. Q because you have to make everything in the voltage, or either you can remove it here. You can write Q here because this has to be in the voltage form. Okay. Now what are how we are going to compute this particular thing? Now there is one assumption. It's a crude assumption, but this is how mathematics basically works. You make some basic assumptions, then you build on the things over it. But I don't personally don't like this assumption because it violates the principle of a quantum well. So what is the assumption? Assumption is that if you have let's say well, if you have, let's say, a rectangular well, rectangular potential well, and if you have solved it, the potential outside is infinite and the potential inside you consider to be zero, you solve the Schrodinger equation for it, you get the solution as psi of x as a sine of kx, where the k is quantized, and it takes the value of n pi over l, where this is the l is the width of this quantum well. Okay, and n belongs to not zero, it belongs to integers 1, 2, 3, so on and so forth, and cannot be zero because you have to have at least one energy level. Okay, so so using this particular rule, or you using this particular solution, you get discretized energy levels, n equals to 1, n equals to 2, n equals to 3, so on and so forth. But note that here the the quantum mechanics says that this particular n equals to 1, it's not exactly at the bottom of this conduction band. This is basically the conduction band of the well. It's not at the green position. So it is very weird to basically absorb at the first stage, because initially what you think is that if you have a structure like this, let's say this is not gas, let's say this is aluminum gallium arsenide, this is gallium arsenide, this is aluminum gallium arsenide. It's something called as potential well structures. These are something called heterostructures if you have multiple layers of gas and L gas. When you solve the Schrodinger, you get n equals to 1, n equals to 2 for the electron. Similarly for the holes, so you have the electron wave function, you have the hole wave function here. These are the holes, these are the electrons. But the mysterious thing is that the first energy level is not here, it's above it by certain value. There is some distance here, there is some energy difference between the first accepted value E0 and the bottom of the conduction band. Okay, that's very weird. Okay, so now that the similar thing happens here when you solve the Schrodinger for this potential. Well, the first energy level, one would assume that energy level would be here, but it's not here. It's above the conduction band by some value. It's very small, 0.1 electron volt maybe, or 100 milli electron volt. But it is there, and it is of very important significance in if you do certain optical experiments, particularly if you are exciting with certain electron volt energies, then this particular difference plays an important role. But in the devices people mostly ignore this difference. Okay, they don't care at all what is this particular difference. But if you are a quantum physicist or you are doing experiments in superlattice structures, then or any optical experiment where you are exciting this system with the light, then these energy differences are going to matter a lot. Okay, so now the assumption is that we are assuming here that this particular E0 is almost at the bottom of this particular thing. This is the assumption. That's what I explained it, which is a very crude assumption. So that means this particular difference is now VDI. That means EF minus E0. Okay, and this is just the assumption you have to consider. Now, how are we going to solve it? Basically, we need to compute this is the sheet charge. If it is sheet, that means it's 2D. That means it's per centimeter square. Okay, so it's an areal, AREAL. It's areal. That means it's present in a area, not in a volumetric charge. It's not in per centimeter cube. Okay. So now, how are we going to compute it? You know from your basic device physics as well. You know that if you know the density of state of a particular system and if you know the Fermi function. Now, what are these two quantities? This quantity is number of energy states, basically number of energy states which are present per electron volt per centimeter square, because it's a 2D. So this is basically allowed energy states that are present per unit energy, per unit volume, or per unit area, whatever you have the system. Okay, and Fermi function gives you the probability of finding an electron. Okay, just like if you have many seats in a classroom, and if you have then these seats will basically represent density of states. But if you have only one student in the classroom, then there is a probability whether the student will sit here or it can sit here, or at other seats. That is basically given by the Fermi function. So now if you multiply both of these, you get the quantity which is the electron density as a function of energy. So n of E can be written as a product of the density of states times the Fermi function. So now what we are going to do with it? How much time is left? Okay, we have enough time for the problems. So now what is going to happen? Now, this particular density of states is computed. It's basically computed in K space, or even in real space you can compute it, whatever is it. So you consider a system like this, then you have this is Kx, this is Kz, this is Ky. So basically these K coordinates are just like the quantum numbers of an electron in a crystal. Okay, it's just like if you have a hydrogen atom, you know that the quantum numbers are n, l, m, and the spin quantum number. So this is orbital, azimuthal, magnetic, and spin quantum numbers. So these are just like the address of an electron. Similarly, in the K space, these are kx, kz, and ky. These are the quantum numbers in the crystal system. Whenever you have a periodic arrangement of the atoms, so these are its quantum numbers. So if you go through the basic derivation of it, that is basically taught in the basic device physics course, you get a relation of this density of state. In if you have a 3D system, you get a density of state. If you have a 2D system, you get a density of state. If you have a 1D system, 3D system means bulk. 2D system means if you have confinement in one direction, that is the system we are concerned about, because we have 2D electron gas. Okay, so the 3D system is if you have the system where electron can move in all the directions. A 2D system, just like a quantum well, just like this particular thing, triangular well, electron can only move in x direction or y direction. It cannot move in z direction. That is the confinement in two-dimensional. So you get approximate relation. This thing is proportional to square root of energy. This thing is independent of energy. Okay, and it's approximately basically given by the effective mass times pi over h bar square, and this thing is inversely proportional to the energy. So this comes from the basic derivation of the density of state, how it is computed. It is a little bit of long derivation. You have to use the Schrodinger equation, and then you have to discretize those energy states, so on and so forth. You get this relation, which comes out to be proportional to the square root of energy, independent of energy, and inversely proportional to square root. So what does it mean? What does it mean in 3D? And Fermi function, is it comes from a thermodynamics. It doesn't have anything to do with quantum mechanics. The Fermi function doesn't have, I should say, any quantum mechanical parameter as such, because the Fermi function is 1 plus e to the power some e minus Fermi level divided by kt. It's all a thermodynamic thing. Okay, every time you have something like h bar, Planck's constant, you have to realize that quantum mechanics is involved. But if you don't have those parameters in it in the equation, then there is no quantum mechanical thing. This mostly depends upon temperature, which is a thermodynamic parameter, the Boltzmann constant, the Fermi levels, and other things. These are all determined by the thermodynamics of the system. So the Fermi function is going to look like, if you have a let's say a 3D system first, then we can go to the 2D system. If you have the Fermi function, which is the probability of finding an electron, if you this is the energy scale, then you draw the Fermi function at a non-zero temperature. Okay, so T not equivalent to 0 Kelvin, because at T equals to 0 Kelvin, Fermi function is somewhat like this thing, a step function. But at a non-zero temperature, the Fermi function looks something like this. Okay, where the probability of finding the electron here is 0.5, which is half, this is 1. So because this is a probability, so the values can be from between 0 to 1 only. Okay, it can be between 0 to 1. And this is, let's say, the Fermi level. Not here, it should be exactly at this point. Exactly at this point, let's say this is some energy EF, the Fermi level at which the probability of finding an electron is 0.5, the half. And now you bring in the density of states. You draw on the same curve the density of states, which is g as a function of E. So g as a function of E varies as square root of E for the 3D system. So you draw it something like this. This is directly proportional to square root of E. Now you see, because the n of E is a product of g of E times the f of E. Now when you have the product, that means you have the overlapping region, which looks something like this. So this is the region we are talking about. So this gives you the charge density of the electrons, which is n as a function of E. If you want to compute the overall charge, then definitely you need to integrate it. That means n. If you want to compute n, now it won't be a function of E, because you have to compute the overall charge. Then you have to integrate this thing. You have to integrate g of E, f of E, as with respect to energy, from some, let's say, energy EF to, let's say, E naught, some higher energy. Or let's say, if you want to compute it above the conduction band or above the Fermi level, you can compute it from EF to infinity. You can integrate it. Then it will give you absolute the charge present in this particular charge present at between those particular two energy levels, determined by these limits. Okay, so this is the 3D case. Now what happens in 2D? And now what happens in 2D is, if you have a two-dimensional system, this is some level. That means that this is density of states. It's independent of energy. This is energy. If it's independent, it'll be constant, it'll be flat. The Fermi function is again going to look like this. Okay, this is the Fermi function. And then you see the overlapping region looks something like, not this one. The overlapping function looks like, why am I not using the same color? So this is the overall charge density. This is n as a function of E. Now, knowing this thing, what happens? Where were we? Yeah, we were talking about sheet charge density. If you talk about now computing the overall charge, then you need to integrate this particular system. You need to integrate, this is basically the sheet charge we need to find in this particular system. This is EF. We need to find this sheet charge. So then you need to integrate the density of states times the Fermi function with respect to the energy. The density of state, you know, which is the effective mass divided by pi h bar square into the Fermi function 1 over 1 plus e to the power e minus ef over kt into dE. This is the sheet charge. Now you need to solve this integral. So there are some certain solutions for this integral. You need to approximate this Fermi-Dirac distribution with maybe a Boltzmann distribution for higher energy. So what we do is that we approximate that. Basically, that's what the approximation I was talking about, that if ef minus e naught is much greater than 3 kt, okay, if this difference is much greater than 3 kt, then you can approximately solve this particular integral, and you can write the sheet charge density as q m star pi h of h bar square ef minus e0. This will be the sheet charge present. Okay, so this is the sheet charge which we can obtain from this particular relation, solving the Fermi-Dirac. This is something called as Fermi-Dirac integral, by the way, and it's very common in semiconductors. And you get the sheet charge. Now you have the sheet charge. What you want to obtain? That means if you can just rearrange the terms, and if you want to find, let's say, EF minus E naught, you can write it as pi h bar square, and maybe divided by ns divided by qm star. So this will be basically what we denoted here as the difference VDI. This will be VDI, which is the difference between, basically there's Q charge here in order for everything to be in the voltage. Yeah, that makes sense. Okay, so this will be the VDI. That means how much deeper is that particular eigenvalue, eigenenergy with respect to the Fermi level. So now you have this particular VDI value, and if this is all in Q, then this will go. VDI can be written as pi h bar square and s divided by m star. Does it make sense? H bar has the units of joules second. It will be joule square, second square, kilogram. This will be 1 per centimeter square. So VDI has to be volt, or it is basically joule per coulomb. Joule per coulomb. Joule square, second square, centimeter square, kilogram. You can write it as electron volt. Yeah, it will give you the exactly that joule per coulomb. Joules, centimeter square, kilogram per second square. Yeah, it'll be giving you. So this is the VDI which we needed to compute. This is the difference between the Fermi level and the first eigenenergy. Now that VDI, where we need to use it, about going to the equation, this particular equation, where you want to compute the sheet charge density as a function of gate voltage. Not if I cut it, if I paste it here, then this is the VDI we needed to obtain, and we have found this dipping of first eigenenergy below the Fermi level, and you see that VDI is directly proportional to the sheet charge density. So if your sheet charge density increases, the difference, that means EF minus E naught, will increase. Okay. So that means the difference between the E0, that means this particular difference, if this is Fermi level, this is this thing. If the sheet charge will increase, this difference is going to increase, so that the approximation we made is going to be more and more realistic. So this will be pushed down, and this will be here, not here, because the sheet charge will increase, so it will look something like this. Fermi level will now be higher, this will be here, so this difference will be more than this particular difference. Okay, so this is, let's say, VD1, this is VD2. So VD2 greater than VD1, that means NS2 is greater than NS1. All right, so what next? And what about what we need to find? Yeah, what else we can find from this? So if we know this particular difference now we can use the basic electrostatics in this triangular well in order to obtain other quantities. What are the other quantities? If you have this triangular well again, you have the Fermi level, the first energy level, E0, E Fermi, the charge density. Now, if you approximate this particular because it's a potential. If you approximate this, it's almost like a parabola, but if you approximate it as a linear potential, linearly varying potential, something like this, okay, it will make your life easier, and also it makes it easier for to solve the Schrodinger as well. Okay, because you can have a linear variation of a potential. You can write potential as some a times x, which is a linear function, instead of some a times x square or a times x cube. That is going to mess up with the differential equation. It will be difficult to solve. Uh, which differential equation? Basically, the Schrodinger differential equation, Schrodinger equation. So that's how you make the approximation when you solve the Schrodinger equation. But here, electrostatically, it is also going to make it easier. Why? Because you have the charge which is present like here, the center of this, which is the centroid. I talked about in this session that this distance is delta d, the distance of the centroid, where the charge density peaks, where the wave function of the electron peaks. The distance of its peak from the interface, this interface, is delta d. Okay, and now you have this particular thing, which is the potential. Basically, it's electric field. If you have the potential, you have the electric field, and you can write this particular electric field as some q times charge density divided by epsilon naught. So basically, this is sigma over epsilon, similar to that of that. Okay, and you have this particular, you have qvdi, which is how deeper is it. That's what we have computed. You can exactly write it equivalent to the electric field. Let's call this electric field E. Let's call it E1. You can write it as electric field times the delta D. Okay, because electric field, you have the negative gradient of the potential, so you can rearrange things and you can find the VDI. Okay, now you can write Q times VDI, which will be basically equivalent to Q times NS divided by epsilon naught epsilon S. Basically, epsilon S, the epsilon for gallium arsenide. Don't confuse it with, it's an epsilon semiconductor. Okay, and delta D, you have to keep it like this. And what are the things we have computed from it? We have computed the we have computed VDI earlier. VDI as some function. VDI we have computed as a function of NS, which was something like this. Okay, using the integral, the Fermi-Dirac integral. And now what you can do is that you can write VDI in terms of this particular equation, and then you have to obtain this delta D, the distance of the centroid. And when you do it, you basically have to rearrange. You get delta D to be equivalent to pi h bar square over m star epsilon naught epsilon s. So just put VDI equal to pi h bar, no, not pi h bar square ns m star to be equivalent to q ns epsilon naught epsilon s delta D. The what terms will cancel out? Ns goes, epsilon will come on the other side. I guess there is Q here also. Yeah, there is Q because it's Q times VDI. So this and this will go. So you have delta D, which is the distance of charge centroid. So this distance is important because why is it important? Because it will tell you how much farther is the charge peak away from the interface. And why does it sound important? Because that is the essential thing in the high electromobility transistors. Because the farther this density is from the interface, the interfacial effects or the interfacial scattering effects will reduce, mobility will increase. So that's why this distance is important. And you see that this particular distance is inversely proportional to the effective mass of electron. Now, how does it intuitionally is how it's intuitionally inversely proportional to effective mass? That's a different question, because effective mass is the sum total of all the quantum mechanical effects summing up into a certain parameter, which is effective mass. Because you know that effective mass is equivalent to h bar square dou square e over dou k square, which comes from the it comes basically from solving the chronic penny model and other things. If you have a band structure like this, which is EK diagram, which is the electron dispersion figure, so the curvature of this is related to this particular denominator. So higher the curvature, lesser will be the effective mass. Lower the smaller the curvature, higher will be the effective mass, so on and so forth. And that is going to impact this particular distance. Okay, so that means what it means is that if you have a if you have a if you have a conduction band and this is a valence band, this particular bottom is the conduction band, this particular top peak is the valence band. So this is E versus K I'm talking about. Don't confuse it with E versus X. So what will happen? That means if you have an electron here, let's say you have another valley here. This is a valley. Let's say this is named as gamma valley. This is named as X valley. So if an electron can go from this valley to this valley, something called as satellite valleys, what you might have studied in the gun effect, then there is a different effective mass here. If let's call it M1, let's call it M2 here. So the M1 is not equivalent to M2. Okay, it depends upon the curvature. So this is curved more, so effective mass will be lower. That means M1 will be greater than M2. Okay, that is the concept of the effective mass. It depends upon the inversely proportional to the curvature. Basically, dou square E over d dou k square, which gives you the curvature of the bands. That means if you have an electron in the satellite valley or gamma valley, which is having M1 greater than M2, that means that particular charge density, if the charge density arises because of the electron present in the gamma valley, that will give the delta D1 less than delta D2. That means the effective mass is going to impact the distance of the centroid from the charges. Okay, so how does it intuitionally impact the charge? That's a different story, but let's move forward. What are the other parameters we need to compute? Okay, what are the other things? Okay, we have computed the distance and the typical values. If you talk about if you have the gas L gas based structure, gas L gas based HEMT, then if you have this as the centroid, then this particular distance typically is 5 to 8 nanometers in gallium arsenide. But if you have LGAN, aluminum gallium nitride and gallium nitride based structure, then this particular centroid distance is 2 to 3 nanometers in GAN algan based hydrogen structures. Okay, so that is just a little more detail about it. Now, what else we need to cover in it? Let me check. Where are we? Yeah, we have covered this. Yeah, there is something called as, yeah. Now we needed to find, from using this equation, we need to find the charge density as a function of gate voltage, because that is the fundamental thing. You want to control this 2D electron gas with the gate present at this end, metal. You want to apply voltage so that you can deplete the electron, you can turn the field effect transistor on and off. So for that you solve this equation, you put the value of VDI, you keep other terms as it is, phi B, delta EC. When you rearrange this particular equation, what you get is an equation which looks something like this. Because you need to compute the NS as a function of VG, you get an equation which is Q ND plus D delta. What are these D delta? I'll talk about epsilon S epsilon naught VG minus phi B over Q minus delta EC over Q divided by Q times D. So this is the equation you get as the source, the sheet charge as a function of gate voltage, how it's going to vary as a gate voltage. And there is something called as lever's rule. Lever rule. Lever rule basically says that if you apply the gate voltage exactly equal to this bracket term, phi B by Q minus delta EC by Q, then you will be having the sheet charge density as Q and D plus D delta divided by QD. What are these other quantities? So if you have a delta doped region, then this thickness is basically capital D, and the distance of this is particularly, let's call it small d. Let me check the nomenclature whether it should match with the equation. It should not mess up. Yeah.
the equations. Yes.
Okay, so this particular this particular thing here is delta doped, which is the L gas region, and you have the charge, not like this. Okay, I need a smaller rubber. Yes, that is going to do the job. You have a sheet charge, which is a two-dimensional electron gas. Then the distance from the distance or the thickness of the aluminum gallium arsenide, let's call it d, small d, and the distance of the doping, delta doping from the interface, let's call it ds or d delta. Let's, because I have used here d delta, let's call it d delta. And this particular distance, which is the distance of this interface to the centroid of the charge, let's call it capital D. Basically capital D is d plus delta d. Delta d is this particular thing, centroid, which we obtained using this equation. Here it is. So that is the overall capital D. So you see that sheet charge density as a function of sheet charge density, if you apply the gate voltage exactly equivalent to this particular term in the bracket, that varies as this particular term. Or let's, if you talk about this entire equation, then it shows that if you go on increasing the D, that means D plus delta D increases, the sheet charge as a function of gate voltage is going to reduce. That means if you increase this particular distance, okay. And what is going to happen if you increase, let's say, D delta, if you are going to increase this particular D delta and ND plus, they are going to have the impact on this sheet charge density accordingly. Accordingly, as directly proportionality and inversely proportional with the distance of the sheet charge from the gate. You have the gate here. This is the metallic system, metal. Okay, and the structure exactly is like this. This is L gas. This is gas. This is 2D electron gas here, and this is the metal. So if you invert this, what should I call, counterclockwise 90 degrees. So this is the band diagram of it. Okay, now I hope you got it. You have a band diagram of this. Okay, all right. Now what else? This I covered. What else is there? This is this basic thing. Now, yeah, now few more things, then we will jump to the questions. I basically don't need these pictures. I can just scribble everything. Oh God. So now what are the other things? Now we are going to talk about resistances inside this device, particularly high electromobility transistors. Now, first question is, where does this resistance come from? Obviously, it comes from the impurity scattering. It comes from the phonon scattering. Impurity scattering, we found a solution that if you delta dope it, you can at least, I should say, reduce it to an appreciable value where the impurity scattering basically reduces. Whether resonant tunneling can occur in this case, whether might the current magnitude. Okay, what is the question? Let me just read your question. Whether resonant tunneling can occur in these cases, what might the current magnitude in that case? Resonant tunneling. Okay, where can resonant tunneling happen? Let me think. So you mean if you have a this L gas here, then you mean to say if you have a gate, then now tell me where will the resonant tunneling happen? Tell me the direction. This is left, this is right. Faster, because we are running out of time now. Left to right. Okay. So you mean a tunneling from this to this end, right? If you can speak, that will be better because that will be fast. communication method. Hello, since the energy levels are aligned. Look, at level the energy levels are aligned. Your thought is absolutely correct, but that doesn't mean that tunneling will happen because this particular thickness is huge. It's approximately 20 to 30 nanometers most of the times, or even maybe up to 50 nanometers. That is first point. That means if you have an electron in the metal, electron as a wave function, it won't be able to tunnel here. For the tunneling to happen, this particular thickness should be approximately 5 or maybe 5 to uh, crude values, approximately let's say 5 to 10 nanometers. Very thin barrier should be there. Okay, wait, anyways, I'm trying to explain it. So the first reason is that tunneling will not happen because it's a very thick barrier. There should be a thin barrier for the tunneling to happen. Okay, so electron will not tunnel. That is first point. The second point is that when you if you want to reduce something called as contact resistance, something called as RC, then what you do is that you want to make it as ohmic as possible because this is a Schottky barrier phi b. Then you want to make it as ohmic as possible. You can see because if the electron has to go from this metal into this thing, okay, then electron has to go over the thermionic barrier. It has to go over the barrier. Okay, so what you do, you can you can basically dope this particular region so that you can bring the band down there. You get a band like this, then you follow it like this. Am I making it correct? Yeah. uh, yes, like this, and then it becomes like this. So if you have a gate terminal here, now the electron, if the electron is at a very high energy level in the metal, now the electron can tunnel this barrier and it can reach onto to the conduction band, and then the bending will bring it down. If in case you want a conduction to happen from the gate, that is one possible scenario. Otherwise, this barrier is so thick that the tunneling will not happen, at least not up to certain electric field value. Okay. And one more thing is that tunneling is temperature independent. Temperature is not even going to play any role. So that is the thing. But people tell there will always be leakage current between the gate and the channel. Yes, that is the leakage current. This particular thing is the leakage current I'm talking about. You don't want the current to flow from the gate terminal. Okay. You just want to gate to modulate the barrier. Okay. You don't want current to flow. Whenever you have the structure like this, you have a gate, you have L gas, you have gas, and you have 2D electron gas. You don't want a current to flow in this direction. No, that is a bad thing. In field effect transistors, what is going to happen? You will lose the control over on and off. You just want a field effect. That is what field effect is. You want the electric field. Let's say this is negative field. Let's say this is gate, and you apply a negative charge on it, negative potential on it. It developed a negative charge over it. This electric field now is going to repel these particular electrons. It's going to deplete it. That's why it's called as field effect, because the field is going to affect it. There will be no direct charge flow between these two terminals. But sometimes the leakage can happen. Okay, leakage can happen in terms of this tunneling. If this tunneling can happen, or let's say the electron gained much energy and it went above the barrier as a thermionic emission, then that electron may come here, it will go down, then it will result in the flow of current in this direction, opposite to that of the electron motion, which is bad, which is the leakage current, what you are talking about. Otherwise, the current should only flow between the source and drain terminal, which are present in a device like this. If this is a device, this is, let's say, L gas, gate. So you have a source here, drain here. So this is 2D electron gas. So you have the current flowing in this direction, that is modulated by this gate. Negative, positive. Negative electric field repels electron, turns it off. Positive field brings the back, or zero field brings it back, and you apply some voltage here. Let's say positive voltage, ground it, positive, negative. You ground this thing, and you have the electrons flowing in this direction, current flowing in this direction, which is the drain current. All right, kindly discuss some assignment five questions. Yes, now I'll go to the assignment five questions. Yes, I'll go to that. But assignment five questions are mostly what I have covered in this session, so you don't need to worry about the assignment questions.
Hello.
Yeah, yeah.
Uh, Bhaiya, so at the interface, this depletion region width can vary. Like in the diagram you had wrote
Which
at
specifically you are talking
bottom.
about? Yeah, obviously, because you're depleting the channel of electrons with the help of the gate. That is what you found in this equation. That's why this equation is necessary. That means how the sheet charge is going to behave with the gate voltage. As you go on increasing the gate voltage in the negative direction, the channel is going to turn off. The sheet charge is going to move away and away from the interface, and you will have depletion. That is what the depletion means. That this channel is going this region is going to go further and further, and it will when it will reach this thing, it will pinch off, something called as pinch off, and you will
Like
have
the above diagram of this.
which
There
diagram?
is this one.
This one. Yeah,
Yeah,
what?
which you wrote.
Yeah, that's what
The
I'm telling
tunneling
you.
current. There, the width is smaller at the top. So at at the bottom, and there is a big gap
Mhm.
at the bottom. So how can it is physically represent, like it's a top surface, the barrier will be smaller or like that?
You are talking about this, if I'm correct, right?
Yeah, yeah, yeah. Yes.
Let me try it. On a different page. So this is like this I'm talking about, or even rather a better representation, schematic representation will be something like this. So what I mean is that there is a huge some charge density here which is bringing this band down, so that this thickness now is lower, so that the electron can tunnel to the other side. And because there are states of aluminum gallium arsenide here, electron can sit, that's why it can tunnel, and then it can roll down, and then it can go into the this particular thing. But uh it's a bad effect. It should not tunnel. The current should not flow towards the from the gate towards the inner part of the materials, the inner part of the basically devices. Okay. So what is your doubt now?
Like at the bottom, the width is very smaller, and
Yes.
at the top, there is width is small. Like
Why isn't it possible? What is the this is just like ulta of this triangular. If this is possible, then this is possible. This is also a triangular. This is also a triangular thing.
okay,
These are
like
bands.
from the difference between the green and black line at the bottom, that width is very big, right? Like 20 nanometer around.
You are talking about this thing, right?
Yeah, yeah,
This is
yes.
20 nanometer, yes. But this thing is because what is happening?
Like physically, where is 2 nanometer?
I'll tell you what physically I mean to say. Let's consider this was gas, L gas before. Okay, this was 20. Fine. Up to this point, this is fine. Now you bring in some positive charge here, highly doped, huge doping. What does positive charge do? It will bring this band down, because now electrostatic potential energy of electron will lower at this point, because electron will like to stay at this particular region. That's what energy band diagram shows you, where the electron will likely be living or staying. The bands are lower at that position. Okay, so positive charges lower the electrostatic bands, and it becomes like this, and then it will become like here. This is the exact representation. Okay, it brings
Okay,
it
so
down
at
at this
high
position.
energy, it will reduce to 2 nanometer, like
Yeah,
at the top.
exactly. So what happened here now is that this particular stays the same, but this particular up to this particular value where you have, let's say, delta doping or some doping, high doping, this reduced to maybe 1 to 5 nanometers, and it's appreciable for the tunneling to happen now, and then tunneling can happen. Okay, so this is absolutely possible. Got the
Okay,
point?
okay, bhai. Yeah, I got it.
So that is what happens in this particular region, also this particular region where you have the sheet charge. So this depletion, or this width where the sheet charge is present, is rather, it's very small. Okay, considering the bulk region is huge, and this particular region where you have a sheet charge ns, it's very small. So because consider you have we computed this particular distance, which is delta d, and it is approximately I should say 8 nanometers in L gas structures. That means this particular whole region would be around 10 nanometers. So it's very thin region as compared to that of the entire bulk, which maybe 100 nanometers long or 200 nanometers long. Okay, so I have a device. So I was working on a device that was LGAN and that was GAN and that had a sheet charge density of some value. So particularly these are maybe 2 to 3 nanometers. This centroid is 2 to 3 nanometers away from the interface, and in that GAN basically it was modulation doped on this side. It was modulation doped on this side, so that this particular thing was intrinsic GAN. This particular thing was C doped GAN, and then there was other things, there were other layers, leave it. So but this thing is that this thing was all around 200 nanometers, this thing was around 150 nanometers. So you see the bulk region is overall behaving as it is, but it is the change which is happening in a slightly smaller region at this particular thing. Okay, it's a very smaller distance or smaller spatial region where the sheet charge is present. So that is what you need to understand. And these two scenarios are exactly equivalent. This is a very smaller region. Okay, this is a very smaller region. All right, now let's talk about questions, because maybe we are left with maybe a few minutes, but we can slightly extend. And the questions are pretty, I should say, simpler. These are just cakewalk if you have understood the concepts well. So modulation doping in heterostructures leads to uh, it leads to definitely reduced impurity scattering and increased electron mobility. That's the first thing I talked about. Modulation dope, you dope this part so that it stays away from the channel, it stays away from the 2D electron gas, so that the impurity scattering gets reduced. Impurity scattering gets reduced, mobility increases. Why it increases? Because the momentum relaxation time increases, it increases the mobility, and that is the reason. Another scattering basically which I didn't talk about is something called as phonon scattering. Phonon scattering, but this is a very deeper topic. There is a it's an entire research field in itself. So phonon scattering is you have atoms. I'm talking about here only. You have atoms here. So there are atoms present. So these are like springs connected to each other, just like a it's like a oscillator model, just like you had in 12th class or class 11th. Particularly I remember those JE problems where you had a mass attached to a spring, and if you just give it little displacement, it'll start to oscillate back and forth, and you can the same physics you can apply to here in order to compute the frequencies of the phonons, the displacement, and the elastic energy, whatever happens with the phonons, that is basically comes from this particular system. So that's why those basics are very important if you want to understand higher order physics. So what happens is that these atoms vibrate around their mean position at some t greater than 0 Kelvin. Even at 0 Kelvin, there is certain vibrations quantum mechanically, but let's not go into that. But if you have certain non-zero temperature, these atoms vibrate. And what happens if you have now an electron coming from here, it wants to go to the other location, because these atoms are vibrating, that is going to interact with the electron, and this is something called as electron phonon interactions. This is something called as electron phonon interactions. And it is different from impurity scattering. Don't consider these as impurity scattering, because I have shown it as positive charges here, but these are not. These can be just atoms. Okay, but these can be these can be atoms. I have shown it positive charge so that you can just differentiate it from that from the electron. And these are the spring models. These are vibrating, and if you have, let's say, this atom moved up, this atom moved down, this atom moved up, this moved down, then you have a wave. Okay, so this is called as basically this is called as something called as what should I call? This is called as acoustic wave. It's an elastic wave, or rather, a better term will be elastic wave. It's just like a sound wave inside the material, because you have atoms vibrating, you have a sound wave, and that is the elastic wave basically. And if you use quantum mechanics, you can quantize this wave. What does quantization mean? That is a different question. That is something called a second quantization. Let's not dive into it. I'm just giving you a flavor of it. Second quantization is basically if you have a wave, you can go from wave picture to a particle picture using something called a second quantization. Okay, let's not go into that. So if you
So
quantize
here
this,
vibration is also quantized.
yes, vibration, that is what phonon is. If you quantize this wave, you get a phonon. Phonon is a quasi particle. That is the particle. This is quantum mechanically. That is what is called as phonon. So vibrations are quantized, and that quantized, a single quantized particle is called as phonons. Okay. Now that phonon, if you consider that that is a particle quantum mechanically, if the phonon or the that quantized vibration is moving in this direction with a wave vector q, wave vector is just like direction of a phonon. And if you have an electron coming here from this direction, let's say this electron with wave vector k. Now, when the electron interacts with the phonon, now what is this interaction? It's a different kind of interaction. I don't want to go deeper into it, but just think of them like a particle, like classical balls. This electron may go in this direction now. Okay, and now you have all sort of possibilities: phonon coming in, electron may go in this direction, or electron may go in this direction. So you have a maybe a phonon coming in this direction as a q, electron coming in this direction, and electron will go in this direction. So that is the basics of something called as Feynman diagram, what you might have heard about somewhere, Feynman diagram. So he solved this particular problem quite brilliantly. Whenever the particles interact, what is the overall scenario that is going to happen? And this is
Where these phonon quantizations also emit photons or absorb photons.
yes, that's those all weird scenarios happen. Now you go into the particle physics regime. Whenever you have electron, you have photon, you have phonon, you have all sorts of exotic particles. They interact with each other, and they interact with all other things in the material, and that is basically my research domain. So that's why I don't want to talk about it, because I may end up finishing the session by maybe morning. So let's leave it here. So you have these interactions which basically interact with the electrons, and it can impede the motion of electrons. Okay, so just like you have a ek diagram for electrons, ek diagram for electrons, which looks something like this, which you know, the bottom of this is conduction band, this is valence band. You also have ek diagram for phonons, which looks something like this. Okay, and there is a band gap there also. This is something called as phononic band gap. Phononic band gap. Let's call it phononic EG. And that means these values are not acceptable vibrational values in the solid state. And these are unique to a particular system. And this is something called as optical phonons. This is something called as acoustic phonons. Okay, acoustic phonons are two types: longitudinal acoustic phonons, transverse acoustic phonons. Similarly, optical phonons, transverse acoustic phonons, longitudinal acoustic, transverse optical phonons.
But what is difference between optical and acoustic? Like
Acoustic.
acoustic one won't radiate any photon.
No, 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 no. That's not the difference. The acoustic phonon, the acoustic phonon is almost, I should say, like a, what should I say? It almost behaves like a sound wave, and it couples mechanically to the systems, And whenever we are talking about acoustic, that's why the name acoustic is there, because it's almost
So
like
anyway, it's finally just vibration, like
it is
mechanical.
vibration. No, everything is vibration. Even optical phonons are vibrations. But it would have been better if I could have shown you the simulation, because I've done this simulation. You will be glad to see how these atoms vibrate. So these are basically denoting the different sorts of vibrating atoms. So if you have acoustic phonons, that's what I told you. You have longitudinal, you have transverse. In the longitudinal, you have atoms like, if you have a longitudinal wave, something like this density wave, which is having the, that means the atoms are closer here and further apart here. So that you have a wave in which the I should say the like the atoms are moving closer and farther apart in the same direction in which the wave is flowing. Okay, that's the longitudinal. That is just like a sound wave. Sound wave is a longitudinal wave in air. You might have heard about. So atoms move in the same direction in which the wave is moving. But in a transverse acoustic phonon, the atoms move in the perpendicular direction to the motion of the wave. So if the wave is moving in this direction, atoms are moving in this direction, perpendicular. So that's why it's called as transverse acoustic phonon. Optical phonons are optical phonons are different in a way that they are almost the, because they are almost the, I should say, they can couple with light, basically couple with light. How they can couple with light? If you have a dipole, then basically electromagnetic wave can interact with this dipole, and it can turn this around. So wherever you have if you have an atom and it turns around in a weird fashion, you have something called as optical phonons. And these are also vibrations, but in a different sense. So they give rise to optical phonons. Let's not go into
So
detail.
it's like that photon which is interchanging the dipole is like coming as like particle or like wave.
Exactly. Yeah, you that is a different that's a different question. Let's not discuss with it. That is a photon phonon interaction. That is a different question altogether. What is happening at the micro scale, whether it's a wave, whether it's a particle. Sometimes it can be a particle interacting with a particle, and that's what I told you. This is my domain of field, so I can tell you more about it, but I don't want to because this is not related to the course. This part is
Okay,
related to the
okay.
course, the phonons, but I don't want to talk more about it. So let's leave it here and let's talk about the questions. We are running
And
out of
lastly,
time.
one thing, whether these phonons also scatter inelastically and elastically like case in electrons.
Okay, so there are different scenarios. Elastically they can actually interact, but there can be some inelastic effects also. If you have high energy photons, let's say if you have these, where are these? If you have this, you see these optical phonons, and you see that they are higher in energy. Usually, something called as longitudinal optical phonon has energy of 100 milli electron volt. And when an electron goes from a conduction band to a valence band to a conduction band, when it thermalizes back to the conduction band, it can release an optical phonon around 100 milli electron volt energy. This optical phonon can be absorbed by another electron that can go above by 100 milli electron volt. So there are elastic as well as inelastic interactions that happen. Sometimes the energy is absorbed, sometimes the energy is given, and but or definitely overall the energy conservation has to follow. Okay, so there are both elastic as well as inelastic effects taking place.
Okay, okay, bye.
Okay, so now the second question: the two-dimensional electron gas has much higher mobility than bulk. We have discussed it a lot. Why? Because of higher screening effect. What is screening effect? That's what I talked about. If you have a 2D EG, if this is impurity scattering, so this is just like metallic sheet of charge, and you know that a metal has a good screening effect. That means there are a lot of free electrons. Okay, and these free electrons act like a screening to the external field, because there is a field coming from these positive charges. Okay, the electric field emanates from a positive charge, ends on a negative charge. So these sheet of electrons almost acts like a screening effect to the coulombic forces coming from the positive charges. So as a result, it gives a much better mobility. So this is one of the reasons why mobility is better in these high electron mobility devices. Okay, so that is what is something called as higher screening effect. And one more thing is remote ionized impurity scattering is avoided by. Okay, that is what is if you have a let's say modulation in dope thing, then this region is something called a spacer. Maybe I might not have mentioned it. So spacer is used to separate these particular things, and you use this spacer at the interface in order to separate these remote ionized impurity scattering. Okay, so that you can reduce it. So the larger this length of spacer, better will be the mobility. But there are certain trade-offs which basically you need to go back to the equation. What equation? Basically ns as a function of vg, because it depends upon the distance of this spacer, the distance of this delta doped region, or the impurity region, as well as other distances which are important in this particular HEMT. So keeping a spacer at the interface is going to avoid the impurity scattering. So this region is given a name as spacer. Okay. Now what other things? Yeah, this question: the conduction band diagram of a heterointerface of two systems is given by. Okay, which of the following statements is true? So you see that there are two conduction bands. This is conduction band, which one is one? Green is one, conduction band one. The blue is two, conduction band two. And what is the difference? We need to show that which one will be having higher 2D EG concentration. Higher 2D EG concentration. That means N of S concentration. So you see that in the first in the first case, the which one? Green. The green case, the Fermi level is greater above the conduction band. Okay, but in the second case, it is not, I should say, deeper into the conduction band as compared to that of the first. That means what is going to happen if you have something like this? If you have this first scenario, you have the other scenario as this. You see, this is almost the Fermi level is totally penetrating towards into the conduction band and greater into the conduction band. So that if you have a n equals to 0, that will be somewhere here. In this, n equals to 0, not n equals to 0. The E0, the first eigenenergy, will be somewhat here, so that this VBI and VBI are different. VDI, sorry, DI. So that VDI1 will be greater than VDI2. Okay, when that is the case, you know that that particular sheet charge which we computed, that is directly proportional to VDI. Okay, and that means the charge density in case of the which one, the green one, the system one, is going to be greater. The charge density will have the higher 2D Eg concentration, and that is quite similar. That's quite simple from the intuition as well. If you have the Fermi level penetrating more above the conduction band, this region, then it is naturally that this particular region will be having a huge density of electrons compared to that of this particular region. Okay, just like if you have a conduction band, if you have a Fermi level here, and consider the other scenario, if you have a, let's say, a Fermi level here. So obviously the electron density here and the electron density in the other case, this one is going to be having higher density compared to that of this one. Okay, so that is the same, I should say, similar phenomena. But here the important thing is that the difference between the Fermi level and the first eigenstate is of very important consideration, because here, if this eigenstate was not there, let's say if there was no triangular well, then you might have to consider it from the bottom of the conduction band, and anyways that would have given you the same scenario, that the charge concentration in this second case, in this case, is greater than that of the first case. Okay, so that is the overall scenario of this question. Question number 5, the lever rule dictates. Yeah, lever rule dictates the charged density as a function of the gate voltage. So charge distribution between the gate and the channel with respect to the applied gate voltage. So that is the lever rule, which we talked about, I guess. Where did I talk about? Did I talk about it? Yeah, we talked about it here. So we talked about lever rule, which gives the charge density as a function of the gate voltage. Okay. And what else? Let's not talk about these particular facts because it has been covered by the professor, I guess. But field plates, I guess I have not covered. But yeah, field plate, it looks the field plate concept is something like, if you want to modify the breakdown of device. Which device we are talking about? HEMTs. So if you want to modify the breakdown voltage VBR of the device, you use something called as field plate technology. Field plate technology. It's just like using multiple plates, gate plates over one another with the certain dielectrics. If you see this figure, so this is metal, this is again metal, this is again metal, and this is again metal. It's a weird system, but in between there is this dark thing. This is dielectric, and there should be the dielectric should be throughout. These are separated, but this is dielectric. This is dielectric. But on the back, all these three gate plates: gate plate one, gate plate two, gate plate this thing, and this gate. These are all shorted at the back. Now, what happens? What happens because of it? Now, what happens is that now if you have a device like this, you have a gate, if you have a drain, you know that there is electrostatic interaction between this gate and drain. And what happens because of it? This is, let's say, L gas. So what happens because of it? If you have a, let me draw it here because there's no space. Now if you remove this, if you have a gate plate over, let's say you have first a dielectric, then you have a gate plate, and then you have another dielectric layer, and then you have a gate plate. This is gate plate 1, this is gate plate 2. Okay, what is going to happen? Whatever the electrostatic interaction was between the gate and the drain, it is going to now get distributed to these gate plates. Just like, because it's just like the electric field. Okay, because there's a electrostatic field interaction between the gate and the drain. Now if you go on increasing the field plates, now the electric field lines might end up differently on different plates. Okay, from the drain to the, because you have mostly applying positive here, negative here, you apply negative here, so the electric field direction will look like something like this. Okay, so that is going to have an impact on the breakdown voltage that we actually covered in the I guess week 3 of the session. And also, because of this, now it can it can actually modulate the depletion beneath it, because you have a 2D electron gas concentration here. So you can have a, if this is the channel, if this is the gate length, so the beneath the gate, exactly beneath the gate, you might have maybe lower, you might have lower sheet charge density, lowered sheet charge density by applying the negative voltage. And here you might have slightly higher sheet charge density, then slightly more higher sheet charge density, so that the sheet charge density gradually varies throughout the channel. Okay, instead of sudden turning off the device, you can basically tune it by tuning the gate plate, by tuning basically because of the field distribution to the gate plates. So you can tune the sheet charge density beneath it by making it gradual instead of a sudden change, and that is going to have the impact on the breakdown voltage. And also it's going to have the impact on the GM parameters and other parameters which we have talked about in, I guess, lecture 3 or 4. Okay, so now what is going to happen? The electric field profile around the gate is manipulated by means of something called as field plates. This is the field plate concept. And there are other considerations also. We might have talked about something called as gate recess, which has some thermal considerations also, as well as field considerations also, in order to make the device performance better. So this is something called as gate recess. Gate recess, these grooves. Okay, and we also talked about something called as mushroom gate structure, but that increases the capacitive coupling between the source and the drain. Let's not talk about it here, but I think we have covered it in the previous session. Okay, now what else is there? Let's jump to the another question. Maybe they might be related. Okay, the gate transit delay depends upon. Yeah, we have talked about this actually. The gate, not in this session, but in the previous session, we talked about there's a frequency. If you have a source, you have a drain.
Is it gate resistance?
Gate resistance, I guess it should be gate length, it should be channel material, and it should be transconductance. These are the three parts which sound logical to me, because the gate transit time is like how much time the electron will take to pass through the gate length. If this is gate, this is gate length, so this is the gate transit time. Okay, let's call it TG, and it will be equivalent to the velocity of electron, the length of the gate divided by the velocity of electron. Let's call it V sat. Let's call it just V. Okay, velocity of electrons. So that is going to determine the gate transit delay. Okay, so, and also the channel material is definitely going to play a role, because you know that the velocity of electron can be changed with the help of, if you have different material in the channel. Velocity depends upon basically, again, those scattering events, momentum relaxation events, and other things. So if you have a different channel material, highly doped or less doped, that's going to impact the velocity of the electron. Okay, just like the impedance of the electron. And transconductance, again, we have considered in the previous session how the GM depends upon the delay, the gate transit delay, how it can vary the GM. We're not going to again discuss all those aspects again here. And the noise power in a device can be reduced with. This, I guess, we have not discussed in this session, but do I have any equation here? Hmm. Mm, should I discuss it? Which power? What do I think? Then I have to discuss this particular thing. I think this is the last question. Yeah.
By whether noise also discussed,
No, no.
I might have missed then.
I think I didn't go to the noise part. But noise part is not much, I should say, discussed in this section because it's a very.
Okay, I had a doubt that you written at the top that the carrier itself can act as noise. Actually, carrier uses people to reduce noise. For example, in lock-in.
Where have I used? Where have I written that carrier can act itself as a noise? But it
Uh,
can. But I have not written it anywhere.
oh, sorry, it's in the picture actually. Uh,
Where is it? Where is it?
Noise model. Yeah, this one. The dominant source of the noise is the carrier itself.
This thing. Yeah. Look. How should I would just want to make you explain a layman source. Whenever the electron flows in the channel, it is definitely a source of noise. If there is no electron flowing in the channel, there is no noise in the device. Okay. Now the question is why? Because you see that whenever you have a carrier flowing in this direction, these are randomly moving electrons. Okay, so it's not an electron going from this direction to this direction, or just like a simpler case. If that would have been case, the noise would have been almost reduced to zero. But it's not like that. Electron
Okay,
motion is like
this
this.
noise is very less, right? Compared to then kept in electric field.
Just try to understand what I'm telling. So when the electron is moving like this in the channel, when you measure the current or when you measure any of the property, you average it. Okay, you average all the values
Okay.
around this particular value so that these all momentum relaxation events, everything that's actually acting as a noise. If that would have been, if you can somehow eliminate all those quantities, all those scattering and other things, you are going to eliminate, I shouldn't say totally, you are going to eliminate most of the noise. But because this is totally a random process. Okay, that's why whenever you have the quantities like power dissipation, or maybe whenever you talk about currents, they are all average quantity. Even the mobility you talk about, we talk about as an average quantity. It's not a absolute quantity we talk. Whenever we compute it experimentally, we talk it as an average, not the absolute value. So that's why if you might see it somewhere written, you might see it written like this: mobility. It's just the expectation value of the mobility, which is almost similar to that of the average expectation value. And whenever you find the power dissipation and other things, you use something called as time average quantities. You average it over time. Now, what is that? I don't want to discuss statistical and a time average and ergodic processes. That's a different thing. But because of the inherent random nature of these processes, there is the inherent noise present in the system. Had it been not random, had it been a deterministic process totally, then you could have at least eliminated most of the noise. But because of the inherent randomness in this device, there is a noise inbuilt, which is because of the flow of the carrier. Because why? Because you see that this term is here. Where is that? Diffusion. You see that because they are also diffusing, and diffusion is a random process. It's a random process. It's not a whenever you have electron diffusing towards this layer, it's totally a random process. Okay, and you have some when you write the diffusion equation for the electron, how do you write it? If you have, let's say, let's write rate equation, something like dn by dt is d square n over dx square plus some generation minus the recombination, and whether you have, yeah, you have dn. So you have a diffusion coefficient here. Okay, diffusion coefficient. And this diffusion coefficient is from Einstein's relation. It's kt by q times the mobility. Okay, mobility here comes. Now, mobility is a very highly average quantity. And mobility, from the previous relation I talked about, it's what was the relation? Mobility is n, not n. It is some tau divided by m, q tau divided by m. This is again the momentum relaxation time, so you see these quantities are all involved, and because of the inherent statistical nature, so they can go in reverse fashion, and they affect this particular diffusion process also. And when I say it, whenever we take the average quantities, then we have all of the things as average: diffusion coefficients, the mobilities, everything. And that's basically the source of the noise. Whenever you have some random process happening, you have the a hell lot of source of noises happening in the system. That's why if you have some voltage sources like this fluctuating, because whenever you measure a current, if you measure a current something like this current waveform, then you take its average value, which you take like a static this DC value, average value of it. Okay, but there is a noise because there's a difference in the peak values compared to that of this constant value. So that is a source of the noise, and this is a source of noise because of carrier motion, because the current is flowing because of the carrier motion. Okay, I hope you got it. Now there are other sources of noise. There is 1 by f noise, there is thermal noise, there is maybe Johnson's noise. I think they are the same thing. I don't know what the names stand
Yeah,
for.
Johnson and thermal, I think same.
They are the same. I don't care about the names, but there are maybe
Short noise.
short noise. Yeah, those things are there. Names don't matter, but the whatever the concept is behind them, they are different sources of the noise in it. But the main thing is that this particular thing, because of whatever you said, the carrier motion, and you know that
Okay.
this
So this is a non-uniform alternating current, kind of.
yeah, almost everything is this thing. This is all an average because there is a random motion of the electron going on there. You cannot have a device without the noise, and that's why there's noise because of the carrier flow itself. Okay.
Okay.
And that's why this particular equation is just an approximation. This diffusion equation, whatever you call it, rate equation or diffusion equation, it's just an approximation. It's not the exact equation. If you want to know exactly what is happening, you need to solve something called as Boltzmann transport equation, which is a more realistic. It's almost a semi-classical thing, but at least it gives you a good picture of what is happening with the electrons. Okay, this is just an
Okay.
approximate diffusion equation, just an approximation of Boltzmann transport equation. This is a more general thing, but it is semi-classical. Okay, so that is what basically I wanted to say, and that was your question. But what about this thing? Okay, all right, then I think we should then wrap up here because we have overshooted the time already. What things I didn't cover? I wasn't able to cover improving. I think this thing discussed, the field plates I discussed. A little bit about the circuit diagram, but it's quite, I should say, it's not, it's a simplistic thing. Most of the things are, they can be explained in easier fashion, but yeah, and that thing is discussed with professor, I guess. I try to explain most of the things which professor has not explained in the slides sometimes, and because only a 2 hour session, and you have to cover the four to five or six lectures of entire week in 2 hour session, so that makes it difficult. So maybe next time we can discuss more, but that's it about this session. Most of the important thing is that you need to understand the band diagrams and the electrostatics, because if you
Yeah,
understand
it was very important and sometimes it confuses also.
if you just understand electrostatics, but that's it, that's enough for, I will tell you, to a device physicist. If you understand quantum, that is good, but if you are not doing research, if you don't want to go deeper into the quantum, it's not necessary. But if you understand electrostatics, you can play with the devices, because at the end of the day, this particular thing, this is a metal, this is L gas, this is a sheet of charge, this is like a capacitor, where this is L gas, this is metal, this is sheet of charge. So if you know how to handle a capacitor, you can handle this device. If you know how to find its frequency response, you can handle this device. That's all. If you know how to solve a capacitor, how to work with a capacitor, that's it. You don't need quantum. You need quantum here just to get the ns sheet charge. Once you get the ns, you can plug it into the normal classical equation. You don't need quantum for that. Okay. Okay, that's it. I guess we're done with this session, and my stylus is also running low of battery, so we are summing up here. If you guys have any question, you can stay, otherwise we can finish the session. What was I able to cover? These things I covered, this thing I covered deeply, this thing I slightly don't touched, but this thing a little bit, maybe a flavor. This thing I mostly discussed. Okay, that's cool. Okay.
Okay, bhaiya. Thank you.
Seventh and eighth question. Now I discuss what are the seventh and eighth questions. Where is the seventh and eighth question? Six. Oh, this is 9, 10. I guess the seventh and eighth questions were the same. Let me still check if I haven't missed anything.
These questions are not included over here, na? Seventh and eighth question.
Yeah,
I
yeah.
think these
That's
are
why.
diagram oriented.
No, no, no. The seventh question, what I can see on the NPTEL portal is same as question 5, and the eighth question is same as question 6. Right? Am I correct or not?
No,
That's
sir,
what.
there are total 10 questions na, in the
There are total
assignment.
10 questions. I know, but I have skipped the seventh and eighth here because seventh is similar to fifth and eighth is similar to sixth. There is some mistake on the portal. I can show you.
Okay, okay, sir. I will check it. Okay, no
Is
issue.
it different in your case? But that's what it's showing for me.
No, no, sir. I have not checked. I will check it.
But it's same.
No
It's the
worries.
same thing. Otherwise, I wouldn't have
Okay.
skipped it.
Okay, sir, fine. I will do it. I
Okay,
will
sure.
check. Okay, thank you.
Thank you. Do you have any question, or we can just finish the session? These are just theoretical questions, so if you have understood the lecture completely, you can just, these are just the cakewalk. And if this would have been a numerical question, then I would have spent more time on the questions itself. But these are mostly covered in the concepts which I discussed before these questions, these concepts. They are mostly important. So if you have understood the concepts, then the questions are going to be cakewalk. Right. So let me finish this session then. Thank you, and see you in next week, same time, and maybe we'll cover the GAN LGAN based HEMTs. Okay, see you guys. Bye bye.
Bye bye.